Welcome to the deep dive. It feels like everywhere you look these days, products are shouting about using the most advanced AI or advanced machine learning. It's just constant.
It really is.
Uh,
And, for anyone who's been around the block a bit in AI, those terms can feel, well, a little vague sometimes.
exactly. Because AI, in the broad sense, isn't exactly new, right? It's been developing for decades. But the thing that's really changed the game, the major breakthrough in recent years, that's been deep learning.
Unquestionably. That's where so much of the excitement and, frankly, the progress has come from.
So that's what we're doing today, a deep dive specifically into deep learning. This is really for you. If you've got that solid foundation in traditional machine learning, maybe you know your regression and your classification, but you're looking to understand what this whole deep thing is about.
Yeah, our goal is to sort of unpack it, look at the core ideas, some clear examples from the real world.
And build up that understanding step by step. Hopefully, you'll come away feeling like you've got a good handle on it without feeling totally swamped. We've pulled together some really great source material to help guide us.
Foundational stuff, newer research. Should be good.
Oh, okay. So let's start right at the beginning. What makes deep learning deep? Fundamentally, it's a type of machine learning, a subset.
Right. It's not something totally separate.
Not at all. The deep part comes from using artificial neural networks that have multiple layers stacked on top of each other. These layers learn what we call hierarchical representations of data.
And that layering, that's the key, isn't it? It allows for much more complex pattern recognition than you could get with older, sort of single layer models.
Exactly. It builds understanding layer by layer. You often hear it compared to the human brain, specifically the cerebral cortex, which handles our higher level thinking.
Mm-hmm. That comparison makes intuitive sense.
There's actually some interesting neuroscience behind that analogy, too. Researcher Susanna Herculano Husel, she developed this clever way to count neurons accurately.
Oh, right. I think I've heard of her work.
Yeah, and she found that intelligence seems to correlate pretty strongly with the sheer number of neurons in the cerebral cortex, not just the overall brain size. So, like, an elephant's brain is way bigger than ours.
But humans have far more neurons packed into that cortex.
Exactly, which links to our cognitive abilities. And that layered, dense structure kind of mirrors how deep learning works, building up complexity from simple features to more abstract concepts.
So the depth isn't just about stacking layers for the sake of it. It's about what those layers learn, starting simple and getting progressively more complex and abstract. It's a different way of thinking compared to traditional ML, where we often had to engineer those complex features ourselves.
You got it. Okay, let's dig into the core structure then. Artificial neural networks, or ANNs, these are the basic building blocks. Think of them as inspired, very loosely, by biological neurons.
Very loosely is probably the right emphasis there. It's more about the concept of interconnected processing units.
Right, so these ANNs are made of neurons, sometimes called nodes, and these nodes are organized into layers. You've got your input layer, then one or more hidden layers, that's the deep part, and finally an output layer.
In the input layer, that's basically where the data comes in, right? Your features.
Yep, just like in traditional ML, you feed in your features, usually as numerical vectors. The network itself doesn't really care how you got those features, just that they're numbers it can work with.
Which, as you said, is a bit different from traditional ML, where feature engineering was often a huge part of the job. Deep learning can sometimes automate much of that feature learning within the network.
Precisely. Now, connecting these neurons between layers are connections. Each connection has a weight and usually a bias associated with it. And these weights and biases, those are the things the network learns during training. They control the strength of the signals passing between neurons.
Okay, so weights and biases are like the knobs and dials the network tunes to get better. But if it's just passing numbers around, multiplying by weights and adding biases, isn't that just a linear calculation? How does it learn complex stuff?
Ah, fantastic question. That leads us straight to activation functions.
Yeah.
These are absolutely crucial. Their job is to introduce nonlinearity into the network.
Non-linearity. Why is that so important?
Well, think about it. If you just stacked a bunch of linear operations on top of each other, mathematically, you could collapse that whole stack down into a single linear operation. All that depth wouldn't actually add any representational power for complex patterns.
Ah, okay. So without nonlinearity, a deep network wouldn't be any more powerful than a simple linear model like linear regression.
Exactly. It couldn't learn things that aren't straight lines, essentially.
Yeah.
Remember the classic XOR problem? A simple linear classifier like the original perceptron just cannot solve it because the data points aren't linearly separable. You need that nonlinear wiggle room. Activation functions provide that.
Got it. So they allow the network to learn curved decision boundaries and complex relationships in the data. What are some common ones?
Well, historically, sigmoid or logistic functions were common. They squash the output to be between 0 and 1, which is useful, say, for predicting probabilities.
Right, makes sense for classification tasks, but
Yeah.
they have issues, don't they? Something about gradients vanishing.
Exactly right, the dreaded vanishing gradient problem. When the input to a sigmoid is very large or very small, the function flattens out. Its slope, or gradient, becomes tiny, almost zero.
And that gradient is what the network uses to update its weights during learning.
Precisely. So if the gradient vanishes, learning basically grinds to a halt, especially in deeper layers. It makes training incredibly slow or even impossible for really deep networks.
Okay, so that was a major bottleneck. How did we get past that?
Enter the rectified linear unit, or ReLU. Much simpler, actually. If the input is positive, ReLU just outputs the input. If it's 0 or negative, it outputs 0.
So it's linear for positive values, but zero otherwise.
Yep. And the key thing is, for positive inputs, its gradient is constant. It's just 1. It doesn't flatten out like sigmoid. This simple change made a huge difference.
Ah, because the gradient doesn't vanish for active neurons.
Right. This allows gradients to flow back much more easily through deep networks, leading to significantly faster training. The widespread adoption of ReLU was genuinely a critical step in making really deep learning practical.
Okay, that makes sense. So we have neurons, layers, weights, biases, and activation functions introducing nonlinearity. How does the actual learning happen? How does it go from input to, well, a useful output?
It starts with forward propagation. You feed an input example, say an image, into the input layer. The network then passes the data forward through the hidden layers, applying the weights, biases, and activation functions at each step until it produces an output, a prediction, at the final layer.
Okay, so it makes a guess based on its current settings, but how does it know if that guess is any good?
That's the job of the loss function, sometimes called a cost function or objective function. It compares the network's prediction to the actual correct answer, the ground truth, for that input example.
And it calculates some kind of error score.
Exactly. It
Yeah.
quantifies how wrong the prediction was. For example, in NLP tasks like translation or language modeling, a common loss function is cross-entropy. It essentially measures the difference between the predicted probability distribution and the true distribution.
Okay, so we know how wrong the network is. Now, how does it use that information to get better?
This is where the real engine of learning kicks in. Back propagation. It sounds complicated, but the core idea is actually quite elegant.
Lay it on me.
It's essentially an algorithm for efficiently calculating how much each weight and bias in the network contributed to the final error, measured by the loss function.
So it figures out who to blame for the mistake.
Kind of. It calculates the gradient of the loss function with respect to each parameter. Think of it as figuring out, for each weight, if I tweak this weight slightly, how much would the error change and in which direction?
Okay.
And it does this by propagating the error signal backward from the output layer through the hidden layers using the chain rule from calculus. It's like an error feedback loop.
So it sends the error message back through the network, telling each part how it needs to adjust.
Exactly. And once you have those gradients, those directions for adjustment, you use an optimization algorithm to actually update the weights and biases. The most common one is gradient descent.
Ah, gradient descent. The sled analogy comes to mind here, right? Trying to find the bottom of a valley.
That's the one. Imagine the loss function landscape as a hilly terrain. You want to find the lowest point, the minimum loss. Gradient descent takes steps downhill in the direction of the steepest slope, which is given by the negative gradient we just calculated via backpropagation.
And the size of those steps is the learning rate.
You got it. A tiny learning rate means tiny steps. You'll probably get there eventually, but it might take forever, and you could get stuck in a small dip, a local minimum.
But if the learning rate is too big,
Whoosh. You might overshoot the valley bottom completely, maybe even end up higher than where you started, or just bounce around wildly. Finding a good learning rate is crucial.
it's a balancing act. Now, in practice, calculating the gradient over the entire dataset for every single step can be computationally expensive, right?
Hugely expensive, especially with large data sets. That's why we almost always use mini-batch gradient descent.
Okay, what's that?
Instead of using all the data, or just one example at a time, you calculate the average gradient over a small random sample of the data, a mini-batch, maybe 32, 64, or 128 examples.
And you update the weights based on that average gradient.
Exactly. It's a good compromise. It gives a much less noisy estimate of the true gradient than using single examples, but it's way faster than using the whole data set. It makes training much more efficient.
Makes sense. And I've also heard about things like momentum helping with optimization.
Yeah, momentum's a really common technique. Think back to the sled. Momentum helps the sled keep rolling, even if it hits a small bump or flat area.
So it helps overcome those local minima?
It can, yeah. Technically, it adds a fraction of the previous update step to the current one. It helps accelerate convergence, especially in directions where the gradient is consistent, and dampens oscillations. It adds stability and often speeds things up.
Cool. So forward prop to predict, loss function to measure error, back prop to calculate gradients, and gradient descent with mini batches and maybe momentum to update the weights. That's the core learning loop.
That's the essence of it. Now, we've talked about the general structure and learning process of ANNs, but what the really powerful things about deep learning is the development of specialized architectures for specific types of data.
Because a generic, fully connected network might not be the best tool for every job, right? Like
Yeah.
images or text.
Precisely. For visual data, for instance, we need something that understands spatial structure. And that brings us to convolutional neural networks, or CNNs.
Ah, CNNs. These are the ones for images mostly.
Predominantly, yes. They are absolute workhorses for anything involving image and spatial data. They're designed to see patterns in a way that respects the grid-like structure of pixels.
How do they do that? What's the key idea?
Two main ideas, really. Convolutional layers and pooling layers. Convolutional layers use filters, or kernels. Think of them as small windows that slide across the input image. Each filter is designed to detect a specific, simple feature, like a vertical edge, a horizontal line, or a certain texture.
So it's like having lots of little feature detectors scanning the image.
Exactly. And as these filters slide, they create feature maps that highlight where those specific features occur. Then you have pooling layers, often max pooling. These reduce the spatial size of the feature maps, making the representation smaller and more manageable while retaining the most important information, usually the strongest activation for a feature in a local region.
So convolution finds features. Pooling makes the representation more compact and robust to small shifts.
You got it. And you typically stack these convolutional and pooling layers. Early layers learn simple features like edges, and deeper layers combine those to learn more complex patterns, like shapes, objects, or parts of faces.
That hierarchical feature learning again, it makes sense for vision.
Absolutely. And the applications are everywhere. Image classification, telling cats from dogs, object detection in self-driving cars, spotting pedestrians, signs, other cars, facial recognition, and huge advances in medical imaging, like finding tumors in scans or analyzing tissue slides.
Really powerful stuff. Okay, so that's vision. What about data where sequence matters, like language or time series?
For that, we turn to recurrent neural networks, RNNs. These are designed specifically for sequential data. The key idea is they have a memory, a hidden state that gets updated at each step in the sequence.
So the output at one point in the sequence depends not just on the current input, but also on what came before.
Exactly. That hidden state acts like a summary of the past information, allowing the network to capture dependencies over time. This is crucial for understanding language, where word order and context are everything, or predicting the next value in a time series.
But didn't standard RNNs also have some issues? Particularly with long sequences, that vanishing gradient problem again?
You're spot on. Just like with deep feed-forward networks, the gradients in RNNs can vanish or even explode over long sequences, making it hard for them to learn long-range dependencies. If you need to connect information from the beginning of a long paragraph to the end, a vanilla RNN might struggle.
So how was that problem solved?
That led to the development of more sophisticated recurrent units, most famously LSTMs, which stands for Long Short-Term Memory Networks.
LSTMs. Okay, what's different about them?
They have a more complex internal structure, often visualized with gates. Think of it like having little controllers inside the LSTM cell. There's an input gate controlling what new information gets added, a forget gate controlling what old information gets discarded, and an output gate controlling what part of the cell state gets passed on.
So they have explicit mechanisms to decide what to remember and what to forget over long periods.
Precisely. There's this core component, the cell state, often called the conveyor belt, that carries information along the sequence with only minor linear interactions. The gates regulate the flow of information onto and off this belt. This additive structure helps prevent gradients from vanishing quite so easily.
Clever, like giving the network better control over its own memory.
Exactly. And this makes LSTMs and similar architectures like GRUs much better at capturing long-range dependencies compared to simple RNNs.
And the applications.
Yeah.
Still NLP and time series.
Definitely. LSTMs became the standard for many NLP tasks for a while. Things like language translation, sentiment analysis, is this review positive or negative, speech recognition. Also tasks like part of speech tagging, where understanding the context is vital, like your example, the old man, the boat. Is man a noun or a verb? And LSTM can figure that out based on the sequence. And yes, still very relevant for time series prediction.
Okay, so CNNs for grids are NMS-LSTMs for sequences, but I feel like there's been another huge shift recently, especially in NLP.
You are absolutely right. The next big leap, and arguably the current state of the art for most complex sequence tasks, particularly in NLP, are transformers.
Transformers, everyone's talking about them. What's their secret sauce?
The core innovation is the attention mechanism, specifically self-attention. Unlike RNNs, which process sequences step by step, potentially losing information over long distances, attention allows the model to directly look at all parts of the input sequence when processing a single element, say, a word.
So when it's looking at one word, it can directly pay attention to other relevant words, even if they're far away in the sentence.
Exactly. It learns weights representing how relevant each input word is to the current word being processed. This allows it to capture long-range dependencies much more effectively than RNNs. And often they use multi-head attention, which means they run the attention mechanism multiple times in parallel, allowing the model to focus on different types of relationships simultaneously.
That sounds computationally intensive looking at everything all at once.
It can be, but it's also highly parallelizable, which is great for modern hardware like GPUs. And it avoids the sequential bottleneck of RNNs. Another interesting aspect is how they handle words. Instead of whole words, they often operate on subword units.
Subwords, like breaking words down?
Yeah, using techniques like byte pair encoding, BPE. It learns common character sequences. So frequent words might remain as single tokens, but rarer words or new words can be broken down into known pieces. This helps handle large vocabularies and out-of-vocabulary words much better.
Smart. And how are these huge transformer models trained? I hear about pre-training.
Right. It's typically a two-stage process. First, pre-training. This is usually unsupervised or self-supervised, trained on absolutely massive amounts of text data, like a huge chunk of the internet.
Learning general language patterns.
Exactly. They use tasks like masked language modeling, predicting missing words in a sentence, like in BERT, or next sentence prediction. This teaches the model grammar, semantics, facts about the world, all embedded within its parameters.
And then?
Then comes fine-tuning. You take that powerful pre-trained model and train it further, usually supervised, on a much smaller data set specific to your downstream task, like sentiment classification, question answering, or translation.
So you leverage the general knowledge from pre-training and adapt it to a specific need. It's incredible how well that works. That attention mechanism really seemed to unlock something fundamental.
It really did. Overcoming the limitations of RNNs for long sequences, combined with the power of massive pre-training. It's led to the rise of large language models, LLMs like GPT-3, ChatGPT, and others.
Which are powering so many applications now.
Absolutely. Everything from text generation and summarization to incredibly sophisticated machine translation, code generation, various forms of question answering, finding answers in text, multiple choice, and even deeper linguistic tasks like dependency parsing, figuring out the grammatical structure of sentences, and relation extraction, finding relationships between entities in text.
The pace of progress there has been just staggering.
It really has. But, as powerful as deep learning is, we need to talk about the practical side, the challenges.
Right. It's not all magic. First off, the data requirements. These models, especially the big ones, are data hungry.
Incredibly so. They often need vast amounts of labeled data for supervised fine-tuning and even larger amounts of unlabeled data for pre-training.
And all that data, plus the complex models, means serious computational resources, right? We're not training these on a standard laptop.
Definitely not. Training large, deep learning models, particularly transformers, requires significant compute power, predominantly GPUs, graphics processing units. Their architecture is just really well suited for the parallel matrix multiplications that are central to deep learning.
Originally for games, now driving AI research.
Exactly. Pioneering work by folks like Reyna, Sarachon, Krzyzewski really showed how GPUs could scale things up. Training a big LLM can take weeks or months on hundreds or even thousands of high-end GPUs. It's a massive undertaking.
Okay, so data and compute are big ones. What else?
Interpretability. or rather the lack thereof sometimes. Deep learning models are often criticized as being black boxes.
Meaning it's hard to understand why they make a specific prediction?
Precisely. You might get a highly accurate prediction, but understanding the exact reasoning path the model took through its millions or billions of parameters can be extremely difficult. This is a big issue in high-stakes domains like medicine or finance.
Yeah, trusting a decision you can't explain is tough. I remember reading about examples where models pick up on spurious correlations, right? Like confusing an overturned bus with a snowplow just because it's surrounded by snow in the training images.
That's a classic example. It highlights how models can lack common sense or an understanding of causality, focusing instead on statistical patterns, even nonsensical ones. Humans generalize better from fewer examples, especially in novel situations.
And that ties into ethical considerations too, like bias.
Hugely important. Deep learning models learn from the data they're trained on. If that data reflects societal biases, gender biases, racial biases, the model will learn and potentially even amplify those biases.
Like the famous examples with word embeddings where man is to computer programmer as woman is to homemaker.
Exactly those kinds of troubling associations. Or facial recognition systems performing worse on certain demographic groups. It's a critical challenge to ensure these powerful tools are developed and deployed responsibly and fairly. How do we audit the data? How do we mitigate bias in the models themselves? These are active areas of research.
Absolute crucial questions. Any other practical challenges? Overfitting.
Ah, yes, good old overfitting. Where the model learns the training data too well, including its noise, and fails to generalize to new, unseen data. It's always a concern, though interestingly, some massive models seem to defy traditional wisdom and keep improving even when they seem over-parameterized.
But for most models, we need ways to combat it.
Definitely. We use regularization techniques. One very common one is dropout. During training, you randomly drop out, temporarily ignore a certain percentage of neurons and their connections on each forward pass.
How does that help?
It forces the network to become more robust. It can't rely too heavily on any single neuron or pathway because it might disappear at any moment. It encourages the learning of more distributed, redundant representations, which tend to generalize better. Usually dropout rates are between maybe 20% to 30%.
Okay, so lots to consider on the practical side. Looking ahead then, where is deep learning going? What are some exciting future directions?
Well, one interesting area is borrowing ideas from nature again, but this time from evolution. Evolutionary computation approaches are being explored to automatically design and optimize neural network architectures, potentially reducing some of the human guesswork involved.
Using evolution to evolve better AI. Meta.
Kind of, yeah. Another big trend is multimodal AI, models that can understand and reason about information from multiple modalities simultaneously, like combining images, text, audio, maybe even sensor data. Think about a system that can watch a video, listen to the audio, and read captions to get a really deep understanding of what's happening.
That sounds incredibly powerful for interacting with the real world. And what about the efficiency aspect we talked about, making these models less demanding?
Definitely a major focus. Research is ongoing into more efficient models. That includes things like designing more computationally friendly attention mechanisms for transformers,
Yeah.
or techniques like quantization.
Quantization, what's that?
It means representing the model's weights and activations using fewer bits, say 8-bit integers, instead of 32-bit floating point numbers. This drastically reduces the model's memory footprint and can significantly speed up calculations, especially for inference on devices with limited resources, often with surprisingly little loss in accuracy.
Making powerful AI more accessible, that's important.
For sure. So, wow, we've covered a lot of ground today. From the basic neuron and the idea of layered representations,
Through how they learn with forward prop, back prop, gradient descent.
to the specialized architectures like CNNs for vision, RNNs and LSTMs for sequences, and the revolutionary transformers that are driving so much of NLP today.
And we also touched on the real-world challenges: data, compute, interpretability, bias, overfitting, and some ways we try to address them.
It's undeniable that deep learning is fundamentally reshaping countless fields. Many traditional approaches, while still valuable in some contexts, are increasingly being complemented or replaced by these deep learning methods. It really feels like the backbone of modern AI innovation.
Yeah, and connecting it all back, it's more than just code and math, isn't it? Deep learning forces us to grapple with big questions about intelligence itself, how learning happens, and critically, the biases embedded in the data we use to train these systems. Thinking about all this, what really stands out to you? Is it the immense potential or maybe the critical hurdles we still need to overcome as this technology evolves?
That's a great thought to leave things on. There's so much more to explore here. We really encourage you. If something we discuss sparked your interest, maybe a specific architecture, like transformers, or an application area like medical imaging, keep digging into it. This field is moving incredibly fast, and understanding the fundamentals is key.